For our second measurement, I'm going to pull the F33 out of the water, which is my receiver right now. And I'm going to replace it with the B&K hydrophone, which is our unknown transducer. So here's what our second set of data looks like on the analyzer. We're using the ITC5292 as the transmitter and the B&K hydrophone as our unknown transducer. So what you can see is, here's our received chirp. There's a little bit of stuff on the trace here that looks like standing waves, and you can see something here that could be a reflection. Now, it's not as apparent as it was in the first part because the B&K hydrophone is so tiny compared to the F33 that there is not going to be any reflection of the sound off of the B&K hydrophone back to the transmitter and then back to the hydrophone. However, you can get a reflection off of one of the walls of the tank, the back of the tank, or maybe the water surface. So what I'm going to do is, using the trigger delay, I'm going to move the window over this way, and you can see that we've got a cleaner trace here because I've gotten rid of that reflection. So here's our second set of data. And finally, for our last two measurements, I'm going to replace the 5292 as our transmitter with the F33, which we will now use as a transmitter. So I'm just going to push the ITC5292 aside here, and I'll drop the F33 in the water. Here is our last configuration. So we're using the F33 as our transmitter and the B&K hydrophone as our unknown transducer. So what you can see now is that there's some very strong evidence of reflections here, and we can see our first received chirp, and there's something going on here. So we're going to look at it on the oscilloscope where we can magnify it and get a better idea of what's going on. So if we look at our data on the oscilloscope more closely, and I've spread out the time base, so it's 200 microseconds per division. So here is our drive signal, here is our first received signal, and here's the beginning of our first reflection. Okay, so this is the reflection here. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, about 9.6 divisions times 200 microseconds per division gives us about 1.92 microseconds. So if I multiply that by the speed of sound in water, 1,484 meters per second, I get a distance of about 2.85 meters. Well, with two transducers that are 2 meters apart and 1 meter below the surface of the water, I would expect the distance for the sound to reflect off the surface and hit the receiver to be right about 2.84 meters. So that is definitely a reflection off the surface of the water. If we compress the time scale again, and let's increase the magnitude, you can see that there's a little reflection right here. So let's figure out where that reflection is coming from. So that reflection is right about here. It's almost off the screen. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, about 9.8, 9.9 divisions. So we'll multiply that by 400 microseconds per division. So 9 times 400 microseconds is about 3.92 milliseconds. So if we multiply that by the speed of sound in water, we get 5.82 meters. Well, in fact, if you look at where the back of the tank is, it's a little bit less than 2 meters behind the unknown transducer, the B and K. So if we take 5.8, subtract 2 meters from that, which is the distance from the 5292 to the hydrophone, and now we take this and divide it by 2, it's about 1.9 meters, and that's exactly the distance from the B and K hydrophone to the back of the tank. So this is in fact a reflection off the back of the tank to the hydrophone. It's a very, very small reflection because of the anechoic lining. But it's still a tiny reflection that's there that can change our data. So since we now know that this is a pretty significant reflection, and that reflection is probably off of the water surface, what I'm going to do is I'm going to use the trigger delay, and I'm going to move the window. So here's that reflection. As I slowly move the window and get rid of that reflection, watch what happens to my trace here. All those irregularities have gone away. There's still a tiny bit, which is probably due to this reflection over here from the back of the tank. However, because of my limitation of a 2 millisecond time window, I can't quite get a place where only the first signal is coming in. I'm still going to get a little bit of this tiny reflection in, but that's the best we can do under these circumstances. Our last measurement is of the current that we're using to drive our transmitter, and this is done with a resistor that is in series with the transmitter. And so now, because we're just measuring an electrical signal in that circuit, we don't expect to see any kind of delay, and in fact that's what happens. Our transmitted signal here and our signal across the current sensing resistor is right here, and there is no delay. Consequently, there's also no reflections that we have to worry about. Here's our current measurement on the analyzer. So this is the signal across the current sensing resistor. If I move the window around, you can see that the data looks exactly the same no matter where the chirp is, and that's because there is no reflection. So this is our data for the current that's being used to drive the transmitter.